In this video, we're going to start our talk more specifically about nucleophilic substitution. In particular, we're going to be talking about substitution kinetics. As we saw in a previous video for Chapter 5, the kinetics of a reaction are heavily dependent on a couple different factors that we see throughout the reaction, both reactants and solvents and various factors about each of them. So in this video, we'll talk about 4 different factors that affect kinetics. 1, we'll talk about the leaving group, sometimes abbreviated LG. 2, we'll talk about the nucleophile. 3, we'll talk about the alkyl, we'll call it the alkyl halide. Usually this leaving group is a halide, but leaving group to be less specific, the alkyl halide structure, just because we will be, in general, we'll mostly be starting with alkyl halides. And then 4, we'll be talking about the solvent. So let's first talk about the leaving group. So the leaving group is generally a halide. So just to remind you, that's F. So bond to F, bond to Cl, bond to Br, bond to I. And what we see is when it leaves, it generates X minus, X being an abbreviation for a halide. So in order to speed up the kinetics of this reaction, we want to stabilize X minus. We want a more stable X minus, which will enhance the kinetics of the reaction. So what we see is if we write out our 4 alkyl halides, we have RF, RCl, RBr, RI. What we see is that RF is the slowest kinetically, followed by RCl, followed by RBr, followed by RI. And the reason for this is that if we look at the anions that each of these generate upon leaving, we have F minus, Cl minus, Br minus, and I minus. I minus is going to be the, for a couple reasons, is going to be the best or fastest leaving group. It has both the weakest Rx bond, and I minus is the most polarizable. If we think about the polarizability of each of these anions, I minus is not only the largest, but it has the largest electron cloud. To spread around this negative charge is most polarizable, so it can better stabilize this negative charge. If we're looking at the other side of the spectrum, F minus, this is going to be the strongest Rx bond, the slowest leaving group, and the least able to stabilize. We can see F minus almost as a point charge, where it's not polarizable at all. It's a small anion. It can't really distribute the negative charge over a space large enough to make it functionally useful. So next we're going to talk about the nucleophile, and we've already kind of talked about the nucleophile, so this is 2, nucleophile. We've already talked about the nucleophile a little bit. What we'll say is anionic nucleophiles are usually going to be faster than neutral nucleophiles in terms of reactivity, because they are more nucleophilic. So these are more nucleophilic, meaning they are stronger Lewis bases than their neutral counterparts. Neutral, now that is dependent on a couple other factors that we'll discuss, but neutral nucleophiles will still react. They just will be a little bit slower than their anionic counterparts. So let's now talk about the alkyl halide structure. So one thing that hasn't been mentioned, but has hopefully been intuited, is that the center must be sp3. So we can have something like this, we can have something like this, but so these are good. But we can't have something like this. This would be no. This is sp2. So that's a no. That won't do nucleophilic substitution. We can't have something like this, where we have next here. So this is sp2 aromatic. That won't work. And we also can't have something, you know, that is sp hybridized. This won't work as well. So we need to have sp3 hybridized centers in order to do this type of nucleophilic substitution. Now the rate of the reaction will depend heavily. So it depends whether it's SN1 or SN2. And we kind of hinted at the reasoning for this in chapter 5. But what we saw is for SN2, what we'll see is that if we line up, we have a tertiary alkyl halide, a secondary alkyl halide, a primary alkyl halide, and then a methyl alkyl halide. What we see is that methyl is going to react much, much faster than primary, which reacts faster than secondary, which reacts much, much faster than tertiary. So tertiary and secondary are really not favored for, we can almost put these in brackets, really not favored for SN2 reactions. If we look at the SN1 mechanism, and I'll just draw these out. So we have a tertiary center, we have a secondary center, we have a primary center, and then we have a methyl center. If we look at this, we see that the trend is actually reversed. So tertiary is going to react much, much faster than secondary, which reacts faster than primary, which reacts much, much faster than methyl. And we can even put these in brackets and say that these really won't react via an SN1 mechanism. They're so slow that they won't, we essentially say this doesn't happen. Just like for an SN2 reaction, we essentially say that that for tertiary and secondary centers, it doesn't happen because of this steric bulk that's blocking our reaction center. And we'll talk about more of this when we talk about the mechanism in a future video, but the alkyl halide structure can determine the rate depending on which kind of mechanism we're looking at. Now, the last factor in determining the rate or the kinetics of a substitution mechanism are the solvents. So the solvent choice is very important. It can't really dictate between SN1 and SN2 except in one specific case, but it can heavily dictate the kinetics of a reaction. So we see that both are accelerated by polar solvents. Polar solvents meaning they have a dipole, so something like methane is not a polar solvent, but something like water would be a polar solvent. And this is because, as we saw, there's ionic transition states, and this is going to stabilize the ionic transition states that occur in both of these mechanisms. Now this is where they differ. So SN1 and SN2 have different preferences for which makes these reactions go the fastest. So SN1 reactions are going to favor polar protic solvents. Protic meaning that they have a labile hydrogen, a labile proton. So this is something like water, this is something like ethanol, alcohols, methanol, acetic acid, something that has these labile protons, and that helps stabilize the transition state that occurs in an SN1 mechanism. Now SN2 mechanisms favor polar aprotic solvents. So that means there's no H+. So there's a couple traditional solvents that are used for SN2 mechanisms. They're acetone, which has the structure like this. Another common one is acetonitrile. Acetonitrile, which has a structure like this. THF, which has a structure like this. And then DMSO, which has a structure like this. So you'll notice that all of these have poles, they have dipoles, so we can see that we have a dipole here, we have a dipole here, we have a dipole here and here, we have a large dipole here and here, So they're polar, but they're not protic. You'll notice that unlike in the alcohols or water or the acids, there's no labile proton. And the reason that SN2 reactions favor polar aprotic as opposed to polar protic is because we see that polar protic solvents, so protic solvents, will actually compete with the nucleophiles that you're trying to do the substitution with, and they'll actually do solvolysis reactions. So we don't want a solvolysis reaction to occur, which can occur when we have these polar protic solvents. So we avoid them by having a polar aprotic solvent. Now, we usually see that solvolysis reactions are common in an SN1 type mechanism. So usually H2O will be both the solvent and the reactant. Methanol will be both the solvent and the reactant. And that works well because you don't have to worry about competition between the desired nucleophile and your solvent molecule. And just remember, there is one case that we will talk about that you can use this to choose between SN1 and SN2, use the solvent, and we'll talk about that in a future video.